Hello class. Topic 9 is another application. It's on growth and decay. So populations that grow or other populations that might decay. Let's begin with the first task. A culture of bacteria grows at a rate proportional to its size. Now this sentence right here can be translated directly into a math sentence. If A is directly proportional to B, or simply if A is proportional to B, then we can say that A is equal to some constant times B. This is the statement you can write every time you hear in math that something is proportional or directly proportional to something else. So when you see that the growth rate grows at a rate that is proportional to its size, so we need to have a variable that represents the size of the population. Maybe we could say P of T is the population size. And this could be any kind of population that is growing or decaying. It doesn't have to be people or animals. It could be bacteria. It could be amount of water in something that's changing. We have something that's changing, and we're reading here that this growth rate, so the rate at which it's changing, in other words, P prime, this is the growth rate, is proportional to its size. So that means it's equal to some constant times its size. We're going to use T as the independent variable. You could just write this as simply P prime is equal to Kp. The rate of change of population is proportional to its population size. And this is a differential equation. You could also write that dP is dP dt and separate the variables. I'm going to divide by P and multiply by T. Notice, keep in mind that K is a constant. And this differential equation, by the way, dP dt equals some constant times P, is called the exponential growth model. So the exponential growth model, or sometimes called the Malthusian model, you'll see that word in your homework. Now we want to solve this. It is separable, so we can divide both sides by P and have the dP with that side, and then multiply the dt over to the constant side. And then we're going to integrate both sides. So integrate and integrate. And this gives us a natural log of absolute value of P is equal to a K times T plus another constant. Then we're going to exponentiate both sides. Remember this e to the kt plus c. The plus c can be broken off and just multiply to e to the c instead. And then when I get rid of the absolute values on the next step, we have e to the c times e to the kt. And then, of course, you can just call this another constant here in the front. So let's say that our differential equation has a solution that's some constant times e to the kt. All right, so here's the beginning of a model of a model of the amount of bacteria as a function of time and hours. However, there are two unknowns about it. There are two things that make this general. We were never told what this constant in proportionality was to begin with. It's just some constant. So we don't know what K is, and we need to know what A is. Once I find these two values, then I'll have a particular solution. Okay, so let's go back to our prompt and see what else information we have in here. Suppose that initially there are 50 bacteria and that 2 hours later there are 100 bacteria. Okay, so we do have some information. We know that at different times we have different populations. At time 0 there were 50, and at 2 hours later, so time is measured in hours, let's put that here, and population is number of bacteria. 2 hours later, there were 100 bacteria. This data will allow me to find the A and the K in my general formula. Let's begin with the 0, 50. Change the population to 50 at the same time. So I'm just going to be rewriting this formula essentially. Change this to 50. At the same time, you change the T there to 0. So we get A times e to the k times 0, but k times 0 is just 0, and e to the 0 is 1, so this gives us 50 is A. In fact, A will always be the population at time 0. Because when you plug 0 in, that part goes away, you always get A. Now let's see if we can find what K is. So at time 2, the population needs to be 100. So far my model looks like this, by the way. Let's take a moment and pause. It's P of t is equal to 50 times e to the kt. That 50 will stay 50 given this situation, because the initial population is always going to be 50 bacteria. But now we want to find K. The proper variables, I should mention this too. When you look at this equation, the actual variables of this equation are the t, we want that to vary, and the population to vary. For any specific situation, A and K are constant. So we just got to find out what they are, but then they stay that, and then you can let t vary and population covary. Anyway, plug in 100 for the population at the same time that we plug in 2 for the time. Now we're going to solve for K. So divide both sides by 50. So we have 2 is equal to e to the 2k. Natural log both sides, and then divide by 2. So K is equal to 1/2 natural log of 2. So there are several ways that we could write our final, let's see, where do I want to write this? I think I want to write this, I could write this directly beneath, I'll write it here. P of t is equal to 50 times e to the k, k is 1/2 natural log 2, times t. Now this is a perfectly good model that we can use to determine how many bacteria there will be at different times. There are ways to manipulate this. Whenever you have a natural log as part of an exponent where there's an e, then there's going to be some sort of way we can simplify this expression. I'm going to do some rearranging of these terms. Put that there. Put the t with the 1/2. I'm going to get rid of these parentheses. Then I'm going to use the property that we have a coefficient of a natural log. It could be brought up as an exponent on that too. Then we're going to have a cancellation of the e natural log. Okay, so I'm going to back out, put this kind of back the way it was, like this, and then write down what this formula looks like after I do that simplification. So P of t will be equal to 50 times 2 raised to the t-halves. And here's another alternate way to write your model. So this actually answers part 1. They both do. Okay, question 2. Find the amount of bacteria after 5 hours. All right, so once we have a working model and the A and the K have been determined, then we just have to find P of 5 in this case. So let's do that over here. And I'm going to use the bottom one. We know that P of t was 50 times 2 raised to the t-halves. Okay. Keep in mind your order of operations. Do the power first and then times the 50. Don't make the mistake of making this 100 raised to the t-halves. That would be incorrect. And we want to do P of 5. So we're going to have 50 times 2 to the 5/2. And without a calculator, that's really the best we could do. But if I reach for a calculator and I do 50 times 2 raised to the 5/2, we get approximately 282.8. And this was amount of bacteria. Okay, and that answers the second question. And the third question, the time required to reach a population of 2,000 bacteria. Okay, so now I just have to take this same model and change this side to 2,000 and solve for t. So we have 2,000 is equal to 50 times 2 raised to the t halves. We want to solve this for t, so divide both sides by 50. And 200 divided by 50 is, 2,000 divided by 50 is the same as 200 divided by 5. 200 divided by 5 is 40. So we get 40 is equal to 2 raised to the t halves. Now you can log both sides. You can do any log you want. There's lots of ways to do this. I'll do a natural log of both sides. Then I'm going to use the property where that t halves can jump down as a coefficient of the logarithm. This is the whole reason why I wanted to log both sides. So I have natural log of 40 is equal to t halves times natural log of 2. Now I just have to divide by natural log of 2 and multiply by 2. And I get t is equal to twice natural log 40 over natural log 2. And I'm going to reach for a calculator and type this in. 2 times natural log of 40 over natural log of 2 is approximately 10.64. We'll just stop there. 10.64, and this was measured in hours. And that is how long it takes for the population of bacteria to get to 2,000, given this model. Okay, the next step was to use Desmos or some sort of technology to confirm our answers. So I'm going to say y equals. Y equals, we had 50 times 2 raised to the, and I'll use x instead of t, but x halves. Then I'm going to change my scale so we can see what's going on here a little bit better. And here's our model for the bacteria growth over time. It is an exponential curve. Just to show you that we could have done the other form as well, which was 50 times e raised to the, and then we had 1/2 natural log 2. So we had a natural log ln of 2 over a 2, and then that was times an x. There we go. So you can see the other form that didn't get simplified, and that form I'm referring to is the first boxed one that we have right here. So plugging that one in. I don't like that 5, make that look better. And it's the same graph as just doing 50 times 2 to the t halves. Okay, so just keep that red one in place. Now to answer the question with technology, we just say, hey, make a vertical line x equals 5, find the point of intersection, and it confirms that we expect 282.8 bacteria at time 5, which is what we got right here, 282.8. And then the other was, how long does it take to get to 2,000 bacteria? So let me change my scale even more and do a horizontal line y equals 2,000. And find that point of intersection, and you can see we have the approximately 10.64 hours. Okay, let's go to the next task. A fish population in a pond grows at a rate that is proportional to its size with a constant of proportionality of 2 per month. Okay, so this is not saying, this is a constant, this is not saying you're gaining 2 fish per month. It's a 2 unitless per month expression. And the reason why this is kind of a strange unit, but when you put this into the context of the Malthusian model, or the exponential growth model, the fact that we have a fish population growing at a rate that's proportional to its size, that dictates the p prime is equal to some constant times p. Now, p is measured in fish. If k has a unit, it should have a unit so that in the end we get a unit that matches p prime, which is fish per month. And so when you put all the units on this, and the k is a 2, we're being given the k at the start this time. Whereas up here we weren't given the k, we had to find it given the data. But now we're being given k, and it's 2 blanks per month multiplied by p fish. And so when you combine these units together, we get fish per month, which is what our P prime unit is. So that's why we see this strange unit on the constant and proportionality. It's a unit listing per month. It's meant to be multiplied with the fish unit. Let's go ahead and delete that. And also, okay, so this is the rate at which the fish are growing. However, there is a removal of fish. Also, fish are continuously removed from the pond at the rate of 2,000 fish per month. Okay, so we can certainly put this 2 back in. So they're trying to grow according to this model, but their rate of change is they're also losing 2,000, and this is fish per month. I'm just going to write in fish per month for now because this was also fish per month. So we can subtract these and get an overall rate, which is measured in fish per month. So our model looks like this. P prime is equal to 2p and then minus 2,000. And now we want to solve this for p. Now this is going to be, again, a separable differential equation. I will begin by factoring a 2 out. That leaves p minus 1,000. And then divide by 1,000, or divide by p minus 1,000. So we have 1 over p minus 1,000 is equal to, and I forgot the dp, times dp is equal to 2, and I'll multiply the dt to this side. All right, that's after I wrote this as dp over dt. And then I separated the variables. Next, we're going to integrate both sides, and we get the natural log of absolute p minus 1,000 is equal to 2t plus a constant. Now I'm going to skip all those steps of exponentiating and getting the absolute values gone. And so in the end, after I exponentiate and get the absolute values gone and do the breaking up of the e to the a sum, we have p minus 1,000 is equal to some constant times e to the 2t. Now we add 1,000. So here is our general solution, and it's general because we have a constant still that needs to be determined to make this explicit or particular. That's the word I was looking for. Looking back at our prompt, we have supposed that there are 1,500 fish initially. So we do have a point of data. We know that if I were to make a table, right, it would be at time 0 that we have the population is 1,500. So we can plug that information in and try to find A. So we change population to 1,500 equals A to the 2 times 0 plus 1,000. So minus 1,000, e to the 0 is 1, so A is just 500. And so here's our model finally. P of t is equal to 500 times e to the 2t plus 1,000. Okay, so now we will answer the questions at hand. A model for the amount of fish as a function of time in months. So that part is done. Let's go ahead and circle that and call that question 1. Question 2 is the amount of fish after 2.5 months. And we are expected to do this by hand within reason. So we want to find the population at time 2.5. So we're going to get 500 times e to the 2 times 2.5 is 5 and plus 1,000. So this is really the best I can say without technology. But if I do reach for the calculator, why don't we just do this right now together on Desmos. Let's go back over here. Let's change this function to 500 times e raised to the 2x, we're saying here, and then plus 1,000. Okay, here's our growth model. Just change some things here. And we wanted to find the population at time 2.5. We'll just type that in there instead. 2.5. Let's hide the purple. Keep changing our scale. And find the point of intersection. And wow, we have 75,000 fish according to this model. let's go back to here, 75,207 fish, we'll say. Oops. Not sure what happened there. It crashed momentarily, and we lost that figure for some reason. 72,000. Wow. Looks like all my apps crashed. That wasn't cool. I don't know what just happened. Better type that back in. Y equals, it was 500 e raised to the 2x. There we go. Plus 1,000. Then we had to change our scale so we can see things better. And then we had x equals 2.5 and our figure right there. So 75,207. 75,207. And this answers the second question. Third question, the time required to reach a population of 8,000 fish. Okay, so we go back to our model, we change the population to 8,000, and we solve this equation for t. So subtract 1,000, so we get 7,000 equals 500 e to the 2t. Divide by 500, so we get 75, or 70 over 5, which is 14. So we have 14 is equal to e to the 2t. Natural log both sides, and then divide by 2. So we get t is equal to 1/2 natural log of 14. And 1/2 of the natural log of 14 is approximately 1.32, we'll say. And this is in months. And this will answer our third question. Using the technology to confirm, do a horizontal line at y equals 8,000. Find out where it crosses, and you see about 1.32 is when we expect the population to be that. So even though these fish are growing rather rapidly, turns out this is a rather large coefficient in our differential equation, suggesting that we have rapid growth of the fish, even though we are harvesting fish. Even though we were taking 2,000 fish. And keep in mind, I said continuously removing. So that really you have to imagine is like a steady stream of fish leaving. It's not like you wait a whole month and then you remove 2,000 fish, which is really what would happen in reality, right? Is you would harvest the fish at certain moments in time, as opposed to like a steady stream of fish being harvested. Or you can imagine maybe fishermen all in there catching fish at some sort of steady rate, so that at the end of the month 2,000 fish have been harvested. But the fact that we're losing fish wasn't enough to offset the rapid growth rate, and we still have rapid growth even with the harvesting. Okay, let's look at the next one. The next one's similar. Repeat the last scenario, but assume the fish are removed continuously at the rate of 4,000. So we're kind of see what happens if I remove them more quickly. Find a model for the amount of fish as a function of time in months. Then find the rate at which fish should be continuously removed. Okay, so we're going to do the first part here. Get that part there over with. So once again, we have a differential equation that is p prime is equal to 2 times the population, but now we're removing 4,000 fish per month. So let's factor the 2 out to begin. Separate the variables, so 1 over p minus 2,000 is equal to dp, for that again, is equal to 2 dt. Now we're going to integrate both sides. Integrate, and we get natural log absolute p minus 2,000 is equal to 2t plus a constant. Exponentiate, get rid of the absolute values, do other tricks. We get some constant times e to the 2t, and then add the add the 2,000 over. Okay, so we get a general equation that looks very similar to this general equation. The only difference is this has a plus 1,000. This one here had a plus 2,000 when all was said and done. And we still have the same initial population, so when t is 0, we still want a population of 1,500. Right, we're keeping that scenario the same. All right, so plugging in 1,500 for the population, and t is 0, so just e to the 0 we get there, plus 2,000. We're going to get a negative value for a, so negative 500 is equal to a. So our model is p of t is equal to negative 500 e to the 2t plus 2,000. Okay, so the instructions don't really say to do much with this, but we're going to graph it and just see what it looks like. And the only things I need to change here are, we're going to have, this is going to be a negative 500, and this is going to be plus a 2,000. And we have a very different looking graph going on here. Okay, all of a sudden, so we do have the correct initial population, but look what's happening to the fish population over time now. We are dropping down. Eventually it's going to drop to 0, and it does so in 0.69 months. This is suggesting that we are harvesting the fish much faster than they can reproduce, and we are going to very quickly, in under a month, deplete the entire population. All right, so it's good to have a little image here what's going on, even though we didn't ask a question about this. But at 0.69 months, we will lose the entire population of fish. All right, so the next sentence is, find the rate at which fish should be continuously removed so that the population does not change. All right, so in this case, we want to be able to figure out, well, how can I harvest the fish? These fish are reproducing, but I want to harvest them at sort of a rate so that they balance out perfectly and the population number does not change. Well, the easiest way to analyze this is to actually work with this differential equation. And we're going to put an unknown right here. So p prime is equal to 2 times p minus some unknown. We can put, let's put in capital H for how much we can harvest. Whatever, put any variable there, other than the variable that's already being used. And we want h to be a number so that the population does not change in size. In other words, we want p prime to be 0, because if population isn't changing in size, then its derivative will be 0. So we simply have to just change p prime to 0 and solve for h. So h needs to be twice the population. Well, what's the current population? We started at 1,500, so h needs to be 3,000. We can harvest 3,000 fish continuously per month. And if we do that, then we will keep the population in check. We would expect to see no change. Now, really quickly, what would this differential equation look like if I did use that 3,000 figure? And that is the answer for the second question that was asked in the prompt. But let's say h was 3,000, so we have p prime is equal to 2p minus 3,000. Factor out the 2, divide, so we have 1 over p minus 1,500. dp is equal to 2 dt. And by the time we get a solution of this, it's going to be the following. A e to the 2t plus 1,500. And when you plug in the initial population, you get 1,500 is equal to a e to the 0 plus 1,500. And because the initial population right here is equal to this constant that's over here, they cancel, you get 0. And when you solve for a, you get a is 0. And because a is 0, your model simply becomes 1,500. So your solution to the differential equation is a constant solution, 1,500. meaning that it's not changing over time. All right, let's go to the next task. A population of rabbits at a farm changes at a rate that is jointly proportional to the size of the population and the difference between the size of the population and the maximum sustainable population of 2,000. Okay, to be jointly proportional. If I say A is jointly proportional to B and C, then you would say A is equal to some constant times the product of B and C. This is what it means to be jointly proportional to two things. Directly jointly proportional, to be more clear, but this is how we're interpreting that statement. So when we say that the population is changing, so P prime is jointly proportional to the current size and to the difference between the max sustainable population of 2,000 and the population. So this whole statement right here, all of that first sentence translates into this differential equation. And this is called a logistic model. Notice that P prime will be 0 for two different values of P. So if you start with a population of 0, like begin with 0 rabbits and then ask what's going to happen to the population of rabbits over time, well, they're just going to stay 0 because there are no rabbits to reproduce. And if you change this P to a 0, if population is 0, that's going to zero out all of this, meaning P prime is 0, meaning we're not changing anything. The other value of P, for which population prime will be 0, is if P is 2,000. So if you have 2,000 rabbits in this farm, this is the maximum number of rabbits that can be sustained. And that means your population, your P prime will be 0, and you will have P prime will be 0, which means your population will not change, so you're going to stay at a population of 2,000. Any rabbits that die off will be reproduced, and you'll just maintain that 2,000 figure over time. If you were to do I didn't ask you to do this, but if you were to do a direction field here, you would see at height 2,000, you would see a whole bunch of solutions that do things like this. And then up above would do other things, but as long as your population starts off between 0 and 2,000, you're going to see a whole bunch of curves that just grow and approach 2,000 like an asymptote. An unrestricted growth exponential curve goes something like this. It gets steeper and steeper and steeper, much like we saw the bacteria curve. But even bacteria, there's a maximum number of bacteria that can be sustained by any environment. For example, if you put the bacteria in a petri dish, you don't expect to get trillions and trillions of bacteria, or quadrillions, or whatever number is not possible for a petri dish. You would expect the curve to eventually flatten out and follow some sort of maximum level. So really, over in the long term, a growth like this that is unlimited is not realistic. There's very few environments, you can argue no environment, that has unlimited resources to allow for growth to just go out of control without a limit. Now, initially, if you're well below the maximum sustainable level, then initially your growth might look exponential. But as you get closer and closer to that threshold, your population is going to have to flatten out and level off. And this overall shape is called the logistic model. And we're going to see that happen here with this particular, when we solve this particular differential equation. Okay, so it's already prepped to, do they tell us what K is? If they tell us what K is, great, then we can just replace it now, but I don't see any information about the constant of proportionality. I do see that we have some information about how many rabbits there are initially and how many rabbits there are 1 year later, but we're going to have to use that information after I get the model to find out what K is. So all we have to do is just solve this general differential equation. Move that up slightly. I'm going to divide both sides by, well, this is separable, but I have to move all of that to that side and leave the K over on the dt side. So we have 1 over P times 2,000 minus P is dP, I keep forgetting to write the dP, is equal to K times dt. And of course the next step is to integrate. Now here's where, to integrate this, you're going to want to do a partial fraction decomposition. So let's do that work right here in the middle. we have 1 over p times 2000 minus p. We want to break this up into two fractions, 1 over p plus, not necessarily a 1, an unknown over p plus an unknown over 2000 minus p. Right? This was reviewed in our very first topic when we reviewed derivatives and integrals. This is called partial fraction decomposition. So go back and look that up if you're fuzzy on these details again. Now, this is a linear term. It's p to the 1. So above that goes an unknown constant. And this is a linear term. It's p raised to the 1. So above that goes an unknown constant. And now we multiply both sides of this equation. I'll just put the whole equation in parentheses times that denominator, times this denominator here. This should clear out all of your fractions, giving us a statement that reads 1 is equal to, and when I distribute this to here and cancel the, so I'm put it in this fraction here and cancel the p's, and we get just a times 2000 minus p. Then I distribute this to this second fraction and cancel the 2000 minus p's, and I get bp. Now I'm going to plug in different values of p and solve for the a and b. So let's let p be 0. That seems like a good choice because it'll cancel this term right there. So we get 1 is equal to 2000 times a. So that means a has to be, let's write it just below. That tells us that a has to be 1 over 2000. Now let's plug in 2000 for p because that will cancel this term. So if we let p be 2000, that gives me 1 on the left side of the equation is equal to 0a plus 2000b. So just positive 2000b. So b is also 1 over 2000. Okay, so next, we go back to our differential, back to our integration. We're going to decompose this and express it as 1 over 2000. Since a and b are both 1 over 2000, I'm going to factor it out. So we had a was over p, plus b was also over, what was over 2000 minus p. Of course, this was the a and the b both. It was here and here, but I factored it out, so it's now there, just to keep the integration easy. And the other side is kt plus a constant. Okay, so we finished integrating this side, but now we still have to finish integrating this side. We have 1 over 2000 as a coefficient of both of these. Antiderivatives are natural log of absolute p plus, and this one will actually switch to minus natural log of absolute 2000 minus p. That minus shows up because of the reverse chain rule on this, right? If you let u be equal to that denominator, you'll see a negative needs to be generated. And we don't need the plus c because that's on the other side. The plus c is right here. Okay, now we're trying to solve this for p. This technically we have a general antiderivative, but we're going to go explicit. We have an implicit general. This is implicit and general. General because of the plus c, and implicit because the dependent variable hasn't been isolated. We still have the p's to isolate. And the easiest way to do this is going to be multiply both sides by 2000. And then use a log property to combine these into 1. If you recall, if you have log a minus log b, you can write that as log of, I wrote that horribly, log of a over b. A over b is your new argument. So we're going to use that property right here and multiply the 2000 to the other side. So we have natural log of absolute p over 2000 minus p is equal to 2000 kt plus, and I'm going to let the 2000 absorb into that general constant. So I'll just call that c still. You could make the argument that we could let the k absorb the 2000 and call it a new k as well, because we still don't have k or c. Let's leave it not done, just for variety's sake. Let's leave it not done. Okay, now we want to exponentiate both sides. So we have, and I'm going to get rid of the absolute value too. We have 2000, p over 2000 minus p is equal to, and the other side will be, when I do e to this times e to that, this part here is going to become the a. So we just have a times e to the 2000 kt. Okay, we're getting closer. There's a few things we can do now to both sides. I could invert both sides. There's a variety of ways to solve this for p. I'm going to invert both sides, and you'll see why that's going to be helpful in just a second. So we have 2000 minus p is equal to p. Now if I invert this general constant, it just stays a general constant. Technically it's a new one, I could say a2. But when I invert this here, you get 1 over e to that, which is just e to the negative of that. So this is what you get when you invert both sides. We can just call that a still, but maybe a1 and a2, where a2 is the reciprocal of a1. You do notice that every time we do some sort of operation on a general constant, it can just stay a general constant, but it's not the same as the other general constant. And the reason why inverting it was nice was I can now split the denominator p up and say this, that 2000 over p minus a 1 is equal to, I'll just put a again, e to the negative 2000 kt. I'm going to add the 1 and then invert both sides again. So let's have this boxed off. Add 1 to both sides and invert again. Okay, so add 1 over, I'll do this in 2 steps. 2000 over p is equal to 1 plus a e to the negative 2000 kt. Invert both sides. Now to invert both sides, I can't just invert this and invert this. Right? When you have a plus b and I say invert it, it has to become 1 over a plus b. It does not become 1 over a plus 1 over b. Right, so you be careful about that inversion here that we're going to do next. Inverting both sides, we have p over 2000 is equal to 1 over 1 plus a e to the negative 2000 kt. And now multiply by 2000. And we finally have a general explicit solution. This is general because we have the unknown constants a and k, and it's explicit because the dependent variable was isolated. Okay, now we still haven't finished step 1 because we haven't yet taken this information that's given to find out what the a and the k are. So we got to figure out the a and k from this information. Let's start with the fact that, let's make a little table over here. Time and population. At time 0, we're told that there were 10 rabbits, and at time 1, it became 30 rabbits. So let's plug in the 0, 10 first. So 10 goes in for the population at the same time that we plug in 0 for t. So that's just going to be 1 plus a down there. So I'm going to multiply 1 plus a to this side and divide the 10 to the other side and subtract the 1. So we get 199 as a. So our model becomes 2000 over 1 plus 199 e to the negative 2000 kt. So we figured out the a first. And now we're going to plug in the second point, 130. 30 goes in for the population. At the same time, 1 goes in for t. And we get this far. And I want to slowly give myself a little bit extra space here. Let's move a few things around slightly. I might have to cram some things in here to make sure we have room for all of this. Move that up. Okay, I'm going to multiply this entire denominator right over to this side here, and at the same time divide this 30 to that side. So we have 1 plus 199 e to the negative 2000 k is equal to 2,000 over 30, so that's 200 thirds. I sort of wish I had said 40 here in our setup so that we would have a whole number here, but now we're going to subtract 1, divide by 199. In fact, why don't I just make that call right now? I'm going to change your official notes so that this says 40 rabbits, just to make the numbers a little bit easier here. And that means we're going to have, that's going to be a 40, this will be a 4, so this will be just 50, which will be nice. So you have a 40 there, We just get a clean 50 there. Subtract 1, we get 49, and divide by 199. So it's not quite so unpleasant. And now we do natural log, and then we divide by the negative 2000. Or we can simply say that negative 2000k. We can stop right here and say natural log of 49 199ths. Why can I stop there? Because when I go back up here, I can just replace this now with this natural log. If I had solved all the way for k and then gone right here and changed that k, then you would see some cancellations with that negative 2000. Okay, so let's now write our model. We have p of t is equal to, I'm just copying this right here, 2000 in the numerator over 1 plus 199 e raised to the, and we just have negative 2000k is going to become this, but then times t. I'll put the t first. And technically we are done. I'm going to do a little bit of simplification. This t here can be brought up now as a power, and then we can cancel the e and natural log next. So we're just going to have this sitting next to that after I do that final change. So p of t, and this is where we'll stop, is 2000 over 1 plus 199 times 49 over 199 raised to the t. And there is going to be our logistic model. This finally answers step 1. So these logistic models are a little bit trickier to solve and to get to the right point. And this is an easy model to check at least one of these points that it worked. This point here, 0, 10. Right, if you plug in a 0 for t, there we go. Plug in a 0 for t, that's going to make all of this become 1. So we just get 1 plus 199, which is 200. And 2000 over 200 gives me that correct population of 10. Let's test this other one. Plug in 1 for t. If that's a 1, then this fraction is just itself. The 199s there will cancel. We'll have a 49 plus a 1, which is 50. And 2000 divided by 50 does give me the 40. So I can tell pretty easily by hand that this is a model that does in fact go through these 2 points. Now, excuse me, let's plug it in here. That's not what I wanted to do. I wanted to clear all this. New graph. Y equals 2000 divided by 1 plus 199 times 49 over 199. There we go, 199. Thank you. Go outside those parentheses, raise that to the x. Okay, now let's zoom down. You're going to see what's going to happen here. There we go. Okay, so we do see the asymptote as expected. So that asymptote is y is equal to 2000. That's our max sustaining population. So initially it looks like we have unfettered growth. We have unrestricted growth. But as we get closer to the maximum level that we can support, the growth rate has to shrink, and then we approach that maximum sustainability level, which is 2,000 rabbits. And also, if we click on this graph, you can see that we do start, in fact, with 10 rabbits. The other point in question was when x was 1, we had 1 comma 40 as a point. Okay, now we're prepared to answer really easily the other 2 questions. Find the number of rabbits after 3 years. So we just have to take the model and change this x here to 3. Not 13, but 3. Find that point right there, and approximately 504. We'll round up to the nearest rabbit. So P of 3 is approximately 504 rabbits. Yep, okay. And the last question was, what's the time required to reach a population of 1,500 rabbits? For this one, I'm going to do a horizontal line at y equals 1,500. And I know the instructions said to do this by hand, but that's just a lot more repeating of the same kind of solving strategies we did. So I'm just going to use the technology to get our answer. So we can expect a population of 1,500 rabbits at 4.561 years. This was all measured in years. I already forgot the number. Just double checking the unit. 4.561. Right, that green doesn't matter. Hide that green. Oops, put the red, purple back. 4.561. There we go. And this answers the other two questions, question 2 and question 3. Using technology to answer those questions quickly. All right, and this is an example of a logistic model. Required partial fraction decomposition to solve it. And when graphed, you saw the expected curve that follows two asymptotes. So it starts at a population, curves upwards, and then levels off and follows a horizontal asymptote, which is the max sustaining level of the population. And this is the last question here. A drug is metabolized by the body at a rate proportional to the current amount of drug in the body. Okay, so that right there, that's the Malthusian statement. So the drug, we can use a different letter than P if you want. We could do drug, D for drug if you want. Drug is, the rate of change of drug, D prime, is proportional to the amount of drug. So it's proportional to it itself. D prime is proportional to D. So we get this statement. Separate the variables. We have 1 over D times D. I guess one thing I don't like about D's is the DD's. So let's use something other than D for the drug level. And R for drug. So we have this R prime is really a dr dt. It's the rate of change in drug with respect to time. So this is the differential equation. It's the Malthusian model. There's no removal, so no subtraction of anything here. And we're going to separate the variables. 1 over r dr is equal to k dt. Integrate, so we get natural log of absolute r is equal to kt plus c. Exponentiate, we get r is equal to some constant times e to the kt. Skipping a few steps there because we've done them before. And here we have our general solution. The amount of drug is equal to a times e to the kt. So you might think, oh, that's going to be a growth model, but that doesn't seem right because you would think drugs would go down. It's going to turn out that k is negative. We'll see that here in a moment, which means that our model is actually a decay model, which means that the drug disappears over time in our body. So don't assume that just because you see this e to the kt that we have a growth model. It's only growth if k is positive. If k is negative, it'll be decay. And the data should just support that automatically. Now the next bit of data is that the half-life of the drug is 4 hours, and suppose 20 grams was administered. Now a half-life means it's the amount of time it takes for half of the population to remain. So when I say the half-life is 4 hours, the data that we're talking about here, so let's do time and amount of drug. At time 0, we had 20 grams administered at time 0, and the half-life is 4 hours. That means at the 4-hour mark, this will cut down by half, which means at the 8-hour mark, it'll be down to 5, right? You just keep cutting in half every 4 hours. That's what it means to have a half-life of 4 hours. Okay, so now let's go ahead and plug in the 0, 20 into our formula. So 20 for R. At the same time, I plug in 0 for T. So e to the 0 is just 1. So A is 20. So once again, we see that the A is the initial amount. So we have R is equal to 20 e to the kt. And now I want to figure out what the k is by plugging in the half-life information. So 10 goes in for R at the same time that 4 goes in for T. So we get 4k. And we divide by 20. And notice we get this 1/2. That's not surprising. 1/2 is equal to e to the 4k. Natural log both sides. And divide by 4. So this is our k rate here. K is 1/4 of natural log of 1/2. You might remember a trick here with natural logs. I could write that natural log 1/2 as natural log 1 minus natural log 2, and natural log 1 is 0. So I could write it as negative natural log 2. Or you can remember this property, 1/2 is 2 to the minus 1, and then bring that negative 1 down as a coefficient, so negative log 2. So it's very common for this rate to be written the following. K is equal to negative 1/4 of natural log 2. These are the same thing. It doesn't really matter which one you pick. Which means our actual model, not A, it's R. R is equal to A, which was 20, e to the kt. K is negative 1/4 natural log of 2 times a t. Now I'm going to do the similar manipulation of this. I could stop here, and technically this is my explicit particular solution to the differential equation, but I'm going to group the t with put it there with like the negative t fourths, and then move all of that up as a power on the 2, and then cancel the e in natural log. Right, so you keep track of all those pieces. Then you could write it this way: e is equal to 20. I'll go ahead and show those few steps. Negative t halves natural log 2. Bring up the negative t halves as a power, and now I can cancel the e in natural log. So here's another way of writing this differential equation. Now I don't know why I made a mistake here. That 4 turned into a 2 for some reason. Let's fix that issue right now. 4, 4, 4. Okay. Another way to write this, of course, is to absorb the negative, pull the negative off the t-force and do 2 raised to the minus 1, which is a half. So yet another way to write this would be 20 times a half raised to the positive t-force. Now this is a model that you might have been able to just figure out on your own from the half-life information. So when you plug in t equals 4, right, when this t becomes a 4, then this is essentially a 1, and this is saying, hey, take 20 and multiply it by a half. In other words, when t is 4, our population will cut in half. When t is 8, so another 4 years, this becomes a 2, and a half squared just means do half twice. So we cut in half twice when 8 years have gone by. And so you can see why this is, in fact, giving us the correct half-life. Let's stop right here as my either one of these. In fact, really any of these is a good answer to question 1, but I'm going to circle just the last one and say that we have an answer to question 1. The amount of drug 6 hours after it was administered. So now we just have to figure out what R of t is. And R of t is going to be, sorry, we want to figure out specifically what R of 6 is. R of 6 is equal to 20 times 1/2 raised to the 6/4. So I'm going to do that on a calculator. We do 20 times 0.5 raised to the 6/4 is 3/2, which is 1.5. And I get approximately 7.07. And this was measured in grams. So this answers question 2. And then question 3, the time required to reach 1 gram of drug in the body. So now we want R to be 1, and we want to solve for t. So take the equation next to the box 1, change R to 1 gram, and we're going to solve this equation for t. I kind of like using the version with a negative power. Let's do this. Okay. Divide by 20 first. So 1/20 equals 2 raised to the negative t-force. You might say, oh, now divide both sides by 2, but that would be bad. This is 2 raised to the negative t-force. So I need a logarithm to bring that down. So we're going to do natural log of both sides. So we have, and natural log of 1/20 is the same thing as negative natural log 20. Right, using the same reasoning I already explained. You'll see why this is all kind of helpful. Now I can use the log property where this can be brought down in front of that log there. And I'm going to divide both sides. I'm trying to isolate t, mind you. So I'm going to divide both sides by natural log of 2, and then multiply both sides by -4. So in the end, I get t is equal to +4 times natural log 20 over natural log 2. And I'm going to do 4 times natural log of 20 and divide that by natural log of 2. This is about 17.29. And this was measured in hours. And there's an answer to question 3. And maybe the hospital decides that when the drug gets down to that amount that the patient is safe to be released from the hospital. So this model gives them the ability to know how long that might take. Okay, and that wraps up our discussion on growth and decay models.